Yeah, we were doing that.
Movie night.
I don't know why they like oh, they're That's fine.
Because I was like, you know, why we are
I have no clue, guys. I cannot do this. Yeah. Why did they not?
I don't really like that.
I think I said.
All right. More people? All right. So we will do AI as promised. I will take a few minutes to just talk about logistics and stuff. Sorry, this is 190. So I posted the 2024 exam, which wasn't there before. I also posted the questions that are relevant from previous exams. So you can practice with that. So I should say that I did pick out the questions that are relevant. It's not all of them, and you'll notice that I didn't post like 2018, 2019. The person teaching at that time was just doing quite different stuff. There are exams from before 2010. 190 has been around since the 90s, but it used to be that 190 was in C++, so it was completely different. Then it changed in 2011 to C, and then it changed a little bit. 2018, 2019, 2020 was the exam was when COVID just hit. So that was like the first offline exam. You can look it up, but it's quite different. So I've taught this course 21, 23, 24. So, and 21 was also an online exam. So we were still doing the COVID thing. So it's also quite different. So I would say like 2023, 2024 would be the things that the 2025 exam would be the most like. So I did decide to do kind of AI algorithms instead of some data structures and stuff like that. So I pointed out that some of the questions from previous exams are also not relevant this year. So just kind of like to give you an overview of what the 2024 exam was like. So essentially the same kind of thing as 180, right? So a lot of it is just kind of the kind of stuff that you have in the labs, some easy, some not so easy, and then some problem-solving questions that are more difficult. This is just kind of, find the median. That might have been on the midterm. No, yeah, I think it was on the midterm this year, actually. This is just like count particular letter. So count all the letters in the string. So just a for loop with an if statement. So essentially kind of 180, but in C. And there's going to be kind of a few questions that are like that are just saying, like, do you know how to code something, relatively straightforward in C? So here you have something that's a little bit more complicated. So what we want is we want to take something like this and reverse the words. So like multiple ways of going around it. Of course, in Python, it's super easy because you just say split, and then you get the list, and then you reverse the list, and then you make it a string. So in C, it's kind of annoying to do. There's multiple ways of doing it. So you could, if you wanted to, if you used str split for project 1, you could use that. It's, to my mind, I never suggest people use it because it's annoying and it's difficult to do, and most people mess it up, even if they're at a computer. So the way I would do it is I would just like literally say, okay, I'll go to the end of the string, then I'll go back, I'll find the first space, my word is to the right, okay, get that word, put it in the new list. Okay, so like not that easy of a question, I think, especially on paper. But if you approach it systematically, that should be fine. So this one is, so like, is it strictly increasing or not is easy. Here you must use recursion, so that's a little bit more difficult. I'm not going to give out the answer if you want to think about it first. But it's basically in the style of, processing lists and strings using recursion, the kind of thing that we had, around the middle of the semester in the lab. This looks straight out of the lab from this year. It wasn't exactly in the lab last year, I believe. So this is just like the circular queue question from the lab. Now, one thing I usually do is like I try to make it so that like literally memorizing something from the lab shouldn't be that helpful. So I kind of change around the implementation a little bit. So like maybe change around the struct, maybe give you specific instructions about like, no, like don't do exactly what we did in the lab, like use this specific method, something like that. However, preparing for it is just about doing the lab from scratch, right? So like if you do the circular lab, like if you were to do the circular queue question from the lab from scratch, you could do this. Okay. So here kind of one change was like I did it with like characters rather than other stuff like that. Okay. This was the challenge question last year. So this is, I believe, like this is the question that like LLMs mess up. I think last time I tried it with LLMs, it didn't even it didn't even run. It just crashed. If you remember the raised to 21 question from not question, lecture example from last semester. This is basically saying, okay, those are the rules, and you take in a starting position, and you want a guaranteed win, but not only do you want a win, you want a win that you want to win in the fewest possible moves. Now, heuristically, it's not that difficult. But here there is an additional requirement, and the requirement is that you must use the depth first search algorithm. So what does that mean? It means that you're not like solving the question, you're thinking about the question in terms of what we talked about last lecture, right? So you're thinking about the game states of raised to 21 as a graph, right? So what does it mean? It just means that you start from 0 and then the connection. So in raised to 21, you're allowed to say +1 +2, right? So that means that you can go from 0 to 1 and you can go from 0 to 2. And then from here, the opponent could go to 2 or they could go to 3. And then from here, it could go to 3 and it could go to 4 and so on, right? So this is the graph, right? So the states are the sums and the connections are legal moves. Does that make sense? So what the question asks you to do is to construct this kind of graph and then do a breadth first search to find the shortest path. So you need to also keep track of the path from the beginning node to the end. So that was, I maybe should not have put this question on the exam in retrospect. It turned out to be pretty difficult, certainly without any kind of prior precedent. And that was just part A. So part B was like, if you used recursion, now don't use recursion. That was actually pretty reasonable. And then this one, nobody got. So again, like if I were to do it again, I would not put it on the exam without previously announcing that this kind of thing could happen. However, you have been notified. So I mean, I won't do literally that, but like if people are hoping that A star is not on the exam, well, keep hoping. Yeah, got to do something different, difficult. All right. So I'm not. Yeah, I will do a session where I just solve the exam as well. I just don't want to. Like, I want to give you an idea of what it's like. I obviously can't like solve the entire thing right now. Okay. This one I just. I mean, I took the. If you remember, I said that was from the 2024 exam. So you know, you can practice dynamic programming. So there's like a dynamic programming question on, you know, every previous exams. There's some from the lab. If you want more, so specifically for this, you can go to leadcode.com and look up dynamic programming. There's lots if you want to practice that. In general, LeetCode is not a great fit for 190, so I'm not saying go and grind LeetCode right now, but specifically with dynamic programming, you totally could. Okay. So this is just what we did in lecture the other day. So just we didn't actually literally do that the other day. So when we constructed the graph, we did that. So a tree is just a graph, right? So you just construct it in the same way that we constructed the graph, last week. And then hash tables, we're not doing this year because we're doing AI. So Q10 is not on the exam. I'm going to try to, so similarly to the midterm, I think kind of the midterm this year was, quite similar to the midterm last year, except with different questions. I'm going to try to do the same kind of thing for the exam so that you're not kind of blindsided. Again, kind of there's no shortcuts. Like what you got to do is you got to be able to do the lab examples from scratch. You got to be able to do the lecture examples from scratch. That's basically what it is. Sometimes there is, and not sometimes, like always there is like, 5-10 points that are problem solving that are, genuinely challenging. Other stuff, like if you can do the lectures and the labs from scratch, you should be okay. All right. I will post the reference sheet ahead of time in a couple of days. Questions about the exam? All right, so I'm done, by the way, with the lab sessions. So I did lab 9 and lab 10 the other day. I will be coming in, or TA would be coming in place of me every day at 6 until the end of classes, and then we'll maybe reschedule. You're welcome to just come in and work, or you can come in and ask questions. Okay, yeah. So it's in BA 8256 currently. So this is yeah, so this is this schedule. Okay, actually today it's at 6:30, and I think this is Samantha that's doing it today, and then I guess yeah, tomorrow tomorrow we'll see. So tomorrow it's not going to be me because I'm at Nocturne. Well, I'm somewhere else, and then I'm at Nocturne tomorrow. So come to Nocturne if you can get tickets. All right. Okay. So and we'll announce some stuff for next Monday as well, and then probably like more in the afternoon rather than in the evening for after classes end. Yeah.
So is it 6 p.m., 6:30 p.m.? Are those going to be on Zoom as well, or are those strictly in person?
Yeah, those are all on Zoom as well. So Samantha posts the Zoom link a little bit ahead of time, and then for my Zoom, it's always the same Zoom. Yeah. All right. But again, kind of, I think there's like limited value. So like, I think kind of the best thing you can do is just like sit down and work rather than kind of watch me work, because I'm not going to work for you during the exam. So yeah. Okay. All right. So that's that. I think that's all the logistics. So let's talk about neural networks. So we're gonna do so this, by the way, is linked from here. This is this. So this is understanding how feed-forward neural networks see. So this is not ChatGPT. This is more kind of the prerequisite for ChatGPT. So we'll do this, and then we'll do language models Thursday and Monday. So what I want to talk about today is I want to talk about what's called artificial neural networks, kind of a brief explanation of how and why they work. So what are artificial neural networks? So specifically for large-scale high-dimensional data sets. So high-dimensional means that a data point is something like an image, or it's something like a bunch of words where it would be represented using, a high-dimensional vector. We know about words being represented using vectors and images being represented using vectors because we did word vectors in ESC190. We are doing images just now, right? So you can think about them as just vectors. And useful means that what you want to be able to do is input this high-dimensional input and get something useful out of it. For example, like what's in the image, or kind of what's the answer to this question, stuff like that. So I want to talk about neural networks as kind of a statistical model. We'll talk about what that means. And also as what we would call a model of computation. So a model of computation is a way to describe how computation happens. One way to describe how computation happens is Python or C, right? So like how does computation happen? Well, like whatever Python does, that's a description of computation. Artificial neural networks are, in a way, a completely different way of thinking how you would take an input and produce an output. And that's despite the fact that you can implement, of course, artificial neural networks in Python. So here's a picture of some neurons. So those are biological neurons. You have about 100 billion of those in your brain, 110 if you're an anxi. Maybe, I don't know. So those are essentially cells. Those cells can produce electrical pulses. Or like there's also like chemicals going around. So the exact details of that, I'm not going to talk about. What I draw, but the basic idea is kind of like this. So if you have those 100 billion neurons sending electrical pulses and activating other neurons that in turn also start sending in electrical pulses. So Jeff Hinton's idea was, well, like that is how you can do computation in the brain. And we should say we don't really know exactly how cognition works in the brain basically at all. It's a theory. Like what we do know is that neurons fire all the time, and some people, although exam results vary, some people appear to have cognition. So those things like the neurons firing and the cognition probably are related, but we don't know exactly. What we do know is that the visual cortex, so the part of the brain that's responsible for visual perception, does appear to work that way. So that's the work of Hubel and Wiesel. So I believe Wiesel is actually from Windsor, so also a Canadian connection. And what they found is that if you show cats pictures, you can actually identify the neurons that are responsible for particular patterns in pictures. The cat is probably not having a good time here, but nevertheless.
Go to Wix.com and set up your store on a single integrated. The researchers actually.
This is kind of the famous experiment. So
Process of slipping the piece of glass into the projector.
So what you hear there is the neuron firing, if you can hear it. And the cat, so the cat is being shown kind of the circle moving in a particular direction.
Seemed to be working in a way that at first we couldn't understand until we found it.
And the cat, okay, I'll briefly show you the cat. It's over here. So it's basically the electrode is in the cat's brain, and they do find that. That results in kind of a particular neuron firing. So that indicates that yes, like there is a connection between neurons firing and cognition. So the light hits your retina. Because the light hits your retina, some cell activates, and as a result of that, there's neurons that start firing, and that's how we think visual cognition works. So that's in people. So or cats. Let's talk about perception in computers. Here we have various musicians, and let's say that our task is recognizing images that correspond to notable Canadian musician Justin Bieber. Okay, yeah. I did this talk for the first time actually in Seattle. So I put in like Canadian musicians and then like people from Seattle here, if you notice. But yeah, like Bieber is Canadian. This is like Stephen Harper did Beatles covers, if you didn't know. And then yeah, okay. Anyway, actually Beethoven is neither from. Yeah, okay. This is not just Seattle. Anyway, okay. So this is kind of what Justin Bieber looks like to a computer. It's a bunch of numbers, right? So those would be the brightnesses of the pixels in like in each of the pixels. So what we want to know is, okay, so how do you take something like this and say, oh, that's Justin right there, right? So what people thought initially, like in the 60s is, well, like, like we'll just code it up. So we'll kind of, figure out like, okay, like this is like the what Justin's nose looks like, and this is what his eyes look like, and so on. And like if we have enough if statements, we'll figure it out. And that really doesn't work at all. So like people tried for a really long time, and that really does not work like at all. So here is the machine learning approach. So the way we think about it is like this. So we have a data set. So the data set would be couples of x's and y's. So the kind of brackets, that's the standard notation. This is just like the first x, the first y, the second x, the second y, and so on. And the x's could be, for example, pixels. And the y's would be, for example, the labels. So like this is like Justin Bieber, and this is Beethoven, and this is, Paul McCartney, whatever, right? And then the idea is, well, like maybe based on just this data, when we look at a new input vector x, we can figure out what the y is, kind of rather than going from first principles and saying, okay, like this is the shape of the shape of Justin's face. Maybe we can just say, well, like, does it kind of look like Justin? Which is like what people do, right? Like we don't think about it like logically when we try to do perception. So here is the simplest possible way probably that you can do it. This is called the one nearest neighbor algorithm. So imagine that we have a training set, right? So we have, this is so the training set would be the set that you have initially. So we have, how many people know those people? Okay, most people, those are the people. So it's like, it's John, and it's George, and this is Paul, and this is Ringo. So interesting, like you probably can't really tell necessarily that those are, pairs of photos of the same person, because like you need, if you don't know them, you probably need like more pictures in your data set in order to understand that, those are the same guy. They are. So okay. So people change. I think. Anyway, so okay. So here's what you might like to do. So let's say that you have this new input. So this is like the vector x, and you want to know, this is Paul, and you want to know like who is it, right? So one thing you could do is like which image in the training set, so in the set where you know the answer, is this input the most like? And then find the picture that's the most like this one, like maybe it's this, and say, okay, this is Paul. Okay, does that make sense? Yeah. 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 So if we're talking about pictures. Okay. So okay, so let's say that we're doing it like that. How would you know whether two images are alike or not? So one thing you can do is you can just say, okay, like x0 is a vector and x1 is a vector. Well, do the cosine similarity between them like we did in ESC190, right? So you can compute the cosine of the angle. And if this guy is large, then x0 and x1, the angle between them is small. So they're similar in some sense, right? That's not the only way to do it. So you can also compute the Euclidean distance between the endpoints of x0 and x1, for example, right? In practice, what we do a lot of the time is just compute the dot product. So you can say if the dot product between x0 and x1 is large, then x0 and x1 are alike. So that's in a way, so it's going to be useful later on. But the reason we're doing it is, okay, like if it is the case that the magnitudes of x0 and x1 are kind of similar, then it doesn't matter whether you're trying to find the dot product that's the largest or the cosine of the angle that's the largest. They're the same. assuming that x0 and x1 are kind of the same magnitude. As you saw in the lab, if you just divide an image by a constant or multiply it by a constant, obviously that would change the magnitude. It doesn't change the contents of the image. So if the images are approximately the same brightness, then it kind of makes sense to say, well, their magnitudes are probably kind of the same. Yeah.
They're the same. They're
I mean, so like if they're perpendicular, that means they're dissimilar.
like the magnitude would still be the same.
Yeah, but like what we're doing, we're not looking at the magnitudes, right? Look, we're looking at the dot product. So if if they're perpendicular, they're very high dimensional, of course, right? But like if they're perpendicular, that means that they're dissimilar in some sense. If they're parallel, so vectors that are parallel, the angle between them is 0. That means it's like the same picture, possibly with different brightnesses. Does that make sense? Yeah.
So like if you're given a set of images, could you like go through them pair by pair and then figure out the ones which are like the most
Exactly.
perpendicular and see like, oh, these are the most dissimilar?
Okay, so the question is, could you find the two most dissimilar images by looking at which ones are perpendicular? And the answer is certainly you could find the pair of images that are, the most perpendicular to each other. However, like the intuition in high dimensional spaces is different from the intuition if you're thinking about vectors in 2D. So in fact, most vectors in high dimensional spaces are basically perpendicular to each other. So by most, I just mean like you pick two random ones and they're pretty much perpendicular. So it's like the intuition kind of, because like, like you pick two directions on the plane and yeah, they could be perpendicular, they could be not perpendicular. But imagine that you're computing the dot product between two very large high dimensional vectors, right? So what happens? You're saying, well, like it's like this times this, sometimes it's negative, sometimes it's positive, this times this, this times this, this times this. Add all of that up, it averages out to basically 0. So yes, you could. However, most images being high dimensional vectors are basically perpendicular to each other anyway, unless they happen to be very similar. And two, while images, so like if images are kind of close, it makes sense to think about their distance, because kind of like, like if the images are completely different from each other, it's like, is like a sunset more different from a dog than it is from a cat? It doesn't really make sense. Yeah.
Where it says assuming the magnitudes are like both like about 1, is that for the cosine similarity or the dot product?
It's for the dot product, right? So like for the cosine similarity, you're not assuming anything. You're dividing by the magnitudes, right? So like you don't need to assume anything. What I'm saying is that like if they're about 1, then you could just compute the dot product and ignore the numerator.
Right, so the dot product would approach.
No, the dot product could be whatever, right? So the dot product measures how similar they are. So high dot product means high cosine similarity, means low angle, means they're similar. Okay. So, all right. So, what do we need to make this work? Obviously, all images must be the same size, right? Because otherwise you can't compute like the dot product of two vectors that are different dimensions. But if they aren't, you can like scale them or crop them. People do that kind of thing all the time. It must be the case that it actually works. So that would work if the images are what's called registered. So registered means that with faces, kind of similar features like eyes, mouth, nose, whatever, are basically aligned. Because if you're computing like the dot product of like Paul's nose with John's eye, it's not gonna make sense, right? So think about it like that. Like if the pixels are aligned, then we can sensibly do like this pixel times this pixel plus this pixel times this pixel plus this pixel times this pixel, and it kind of makes sense if they're aligned. So if it's basically like a brighter and a darker version of the same image, then yeah, it's going to work. If they're not aligned, the whole thing breaks. So for now, we're just assuming that the images are kind of registered for the faces at least. Okay. So here's a concrete task. So I apologize for switching up the faces of the people. This is just what I had. So let's say we have like, you know, something like this where this is whoever, I think this is Alec Baldwin. I don't know. So this is like those people, okay? And we know that, so we have this as the input data where we know the name, we know like here are all the pictures of Alec and here are all the pictures of whoever this is and here are all the pictures of America Ferrera and so on, right? And then we have a new image and we want to know whose picture is it. So, okay. Before I do that, so the first slide about what do you actually need to know about this. So you need to know what one nearest neighbor means. You could be asked to implement it. Like there's nothing to it, right? Like all you need to do is you need to like take an input and compute, you know, the cosine similarity between the input and every possible data point in the training sets and get the label that corresponds to the largest dot product or the largest cosine similarity. Okay. Okay. So for now, we haven't talked about neural networks. So here is the simplest possible neural network, and we'll talk about how that connects to what we just finished talking about, the one nearest neighbor algorithm. So this is a graph, right? A weighted graph, in fact, and this graph represents the simplest possible neural network. So here's how it works. So the nodes at the bottom represent the 64 by 64 image. So 64 squared is 4096. So you have, you know, 4096 nodes in there. And then what this graph represents is a computation. So you're trying to compute 6 outputs, Z1, Z2, Z3, Z4, and so on, Z6. The way you do it is you compute X1 times the weight here, and then X2 times the weight here, and then plus and so on, X20 times the weight here, and so on, and that's Z1. So this is the formula. So W is this array. So the 1 is always there. And then the weight that connects, for example, X20 and Z1 would be W121. Okay. So there are also B's here. So here, in order to compute Z1, you also add in B1. So you compute this sum. So X1 times this weight, X2 times the weight that connects X2 to Z1, X20 times the weight that connects X20 to Z1, add all of that up. When you're computing Z1, you also add B11. All right. You then, for technical reasons that we're not going to get into, transform this using a monotonic transformation. So sigma is this kind of function. There's like various formulas for this, but it's kind of this kind of function. Okay, so what this is just a way of expressing that sum over there. Does that make sense to people? Yeah. So for now, the 1 is just always there. I'm going to use it in a later slide. But for now, the 1 is just there. It's not doing anything. Yeah. So the W's are constants, right? So the network here is a way to express that formula. We didn't talk about training yet, but yes, right? So the idea is, so what you need to know, by the way, is you have this guy need to, in principle, be able to implement it. So maybe you set up a graph that represents this. So we know how to set up graphs from last week. And then you compute it. So in practice, like for this, a graph would be too much. You probably just want to set up a for loop that just computes this sum, right? Okay. So here's why we're doing all of this. So what we want to say is, okay, so we have those W's and we have those B's, and they're just coefficients. So there are ways of figuring out W's and B's such that as often as possible, at least, maybe not always, if X is a picture of person 1, then the Z is 1 and those are all zeros. And then if it's a picture, if X is a picture of person 6, then Z6 is high and all the other ones are low. The process of figuring out those W's and B's is referred to as training. So we're not going to get into the details of how you do that. We have, however, done something like that in 180 with half-filled networks, right? So we've done it in a way that would not scale because we just like basically like adjusted things heuristically, or on the exam or in the test, you just like look through all the possibilities or something. But there are ways of doing it. Yeah. Yes. So the difference is that the goal for the hub-filled network, if you remember, was to store what we called memories. Here, the goal is we have this network which really represents, a formula, and we want for this formula to actually compute the output that we want, right? So what we're saying is, on the images for which we know the answer, we know whether it's person 1, person 2, person 3, person 4, we want to find the W's and the B's such that usually if you input a picture of person 1 into the X, you get a high Z1 and low Z2, Z3, and so on. Right? Yeah.
So like negative documentation.
So the question is like, would the input be like positive, negative? And the answer is, it can be whatever, right? So so people sometimes do kind of subtract the average so that sometimes they're positive, sometimes they're negative, but it doesn't really matter, right? So if you multiply, so like let's say that you make all the X just darker by multiplying it by 0.5. Well, like the W's could adjust by a factor of 2 up so that it all evens out. So the outputs are between 0 and 1 because I transformed them using the sigma. So yeah, but that's just because we set it up that way. Yeah.
Did we say what the B's are?
So the B's are also coefficients. So here, so the way the formula works is the Z is a weighted sum of the X's plus the corresponding B.
And W is the weight of each like edge in the graph.
That's right. Yeah. So W is the weight of each edge. So for example, this edge is connecting X 4096. So pixel number 4096 and output number 6. Make sense? All right. So training is basically just adjusting the W's and the B's, finding the best W and B, such that the formula that this neural network represents computes the output that you want. And the output that you want is Z1 is high if X is person 1, and Z2 is high if X is person 2, and so on. Make sense? And the remarkable thing is that works. So you just set up a formula. You say, we have this formula, which is represented using the neural network. And the intuition as well, like maybe that's kind of how the brain works, because there's also like neurons communicating there. So the nodes kind of vaguely correspond to neurons. And it turns out that this works. So how would you actually do recognition? So once you found the W's and the B's in such a way that the formula roughly computes the things that you want, you just say, well, like whichever Z is higher, that's what corresponds to the output that I'm gonna get. Yeah.
Like.
I mean, you know, the more data you have, the better it works.
That one is the one after, and there's 100 photos of that one.
Oh, no. So what we're saying is we wanted, so like we are plugging everything in and we're adjusting the formula. So adjusting the formula, I mean, adjusting the W's and the B's in such a way that usually when you plug in something from the training set, it gives the right answer.
So then X1 all the way to X4 is that all the pixels in one?
Yeah, that's exactly right. So so we have a 64 by 64 image that's like a particular photo, and this just happens to be 4,000. Yeah,
Each of the nodes is like one pixel.
that's right.
Then one.
Yeah. Why do you need the B's? Strictly speaking, you can try to get away with not having the B's. One intuition here is that in the particular example that I gave you, it was the case that you have like equal numbers of people of each of the photos. You might imagine a situation where you know that you're like much more likely to see like Paul McCartney's face than my face in, you know, like when you are trying to do face recognition. So you might like to just like up the B for Paul McCartney just to say like, if you're not sure, it's probably Paul, not Mike. Yeah.
Line, I guess, is like the best photo match for that pixel, and then the one with like the most connections to a single photo is like the best match.
So not exactly. So here everything is connected to everything, right? So all the pixels are connected to all the outputs. So it's more that we have this formula, right? And this formula takes in the input pixels and it computes the possible outputs, right? So it computes rather six outputs. And what we're trying to do is we're just trying to find the coefficients such that this formula outputs the right thing on the training set. Yeah. No, so the B's are connected to the Z's, right? Right. So think about it in kind of this formula. So when we're computing ZK, we have this sum of X's, and then we add the corresponding B. One B per Z. There's 6 of them. Yeah.
So each set just represents that sum, or like how does that relate to the actors?
So it relates to the actors by just me deciding I want it to be the case that if the X is a picture of actor 1, then I want Z1 to be high. It's an arbitrary decision about how I number them, right? So I just say, I'm setting it up and I'm specifically trying to find W's and B's such that if I input an X where I know the answer, then I'll get the output that I decide is correct for that. And I just decide that the correct output for actor 1 is 1, 0, 0, 0, and the correct output for actor 2 is 0, 1, 0, 0, 0, and so on.
Like,
yeah.
Like that 8 out of 6 number.
Well, Z6 is the 6th number, right? So like this is like Z1, and then so we are calculating all of them. We're calculating Z1 and Z2 and Z3 and Z4. Yeah, that's right. Yeah. Does that make sense now? Yeah.
Like each individual set Where and then they come into like that's.
Yeah, that's right. So I'm just like plugging in the X's, getting in the Z's, and reading. If I have 6 people in my training set, reading off like 6 numbers, and then the way I decide what my output is I just look at, which of the Z's is the highest.
Find the X1 that's like.
Yeah, that's like a whole research area of how you find the weights. So there are kind of and I might or might not get around to doing an algorithm, but like you might imagine just trying to say, well, like I'll just change W1 4096 by up by 0.1 and see if that gets me better outputs. And if it does, I'll just keep that. If it doesn't, I'll try minus 0.1.
It's like how.
So it's better than trial and error. Like there's like a way to do it with calculus, but like in a way, part of it is trial and error. So like in fact, often you add randomness to it.
Based on and then.
No, so we are not doing cosine similarity here. So that's like let me just take 1 minute. We'll come back to this next time. But just to make the connection to exactly what you're asking about cosine similarity. So an interpretation of what we're doing here, like all we're doing is like we came up with this formula and we're saying, I just want to find the coefficients that output the right things, right? But an interpretation of this is what Z1 is the dot product of the X's and the weights that correspond to the X's that connect the X's to Z1, right? So it's like X1 times W111 plus X20 times W121 and so on, right? So Z1 is going to be large if this dot product is large. So in that way, it connects, right? So what we're basically trying to do is we're trying to find the set of W's. So like if you take like slices of the W such that it works out that if the dot product of X with the slice of W that corresponds to the connection to the Z1 is large, it's after 1. And if the dot product is large with the other slices, that's 3 and so on. So in a way, what we have is like 6 vectors with which we compute the dot product of X of. And we're asking which of those 6 vectors is X the most like, in the sense that the dot product of X and that vector is the largest. And you can visualize this vector, these vectors, this is what they look like. So the colors are just there for, like those are black and white images, but just like orange is positive, blue is negative. So those are kind of, if you try to get the best possible outputs in terms of predicting the right answer, those are the templates for like Alec Baldwin and Steve Carell and whoever, Bill Hader and American Carrera and so on that you get. You can kind of see they don't look anything like Alec Baldwin or Steve Carell or anything like that, but they do kind of look like faces. And this just comes out of trying to find the best possible coefficient and then taking the slices of the coefficients that correspond to the faces. So I'll just show you a preview of something like this. So those are templates that you automatically get by doing something more sophisticated, which is kind of like deep learning. And those really do look like faces, some of them a lot like faces. We'll talk about how to get those kinds of templates automatically next time. All right, I will see you tomorrow. Bye.